Welcome to the deep dive. Today we're looking at a really foundational piece of physics, W.L. Bragg's 1922 Nobel Lecture. It's called The Diffraction of X-rays by Crystals.
That's right. And this lecture, it pulls together the work that won him and his father the Nobel Prize back in 1915.
And it's work that, it basically gave us the tools to see inside solid matter for the very first time.
It really did. You could argue it's the bedrock of, well, almost all modern structural science. It wasn't just about collecting data. It fundamentally created a new way of asking questions about solids, minerals.
Even biological molecules eventually.
Exactly. The methods they developed are still, core techniques today.
So let's set the scene a bit. It started with Max von Laue, didn't it? He discovered that crystals could diffract X-rays.
That was the spark. And the key insight, maybe a bit of a happy accident, was realizing the scale matched up.
The X-ray wavelength, tiny, like 10 centimeters.
And the spacing between atoms in a crystal, maybe 10 times bigger, but crucially, in the same ballpark. It meant the crystal could act like a natural diffraction grating for these X-rays.
A ready-made one.
Perfectly ready-made.
Yeah.
But Laue's first explanation was, pretty complicated.
How so?
He sort of assumed the X-ray beam itself contained only very specific wavelengths, and those were being picked out by the crystal to create the diffraction patterns. He thought the X-rays were the selective part.
Okay, and this is where the Braggs come in, particularly the younger Bragg, W.L. Bragg.
Yeah.
He looked at this complex picture.
And he had this brilliant simplification. He said, what if we just think about it differently? Instead of complicated diffraction theory, what if it's just reflection?
Like light bouncing off a mirror.
Exactly like that. He imagined the atoms arranged in these neat parallel planes within the crystal.
Okay.
And he treated these planes as, like, semi-transparent mirrors. So an incoming X-ray pulse would reflect off successive planes.
And this changes the perspective, right? It suggested the X-ray beam didn't have to have specific wavelengths. It could be continuous, like white light.
Precisely. And the crystal structure itself, the spacing of those planes, would naturally select and reinforce certain wavelengths through constructive interference, where the reflections lined up.
So the crystal becomes the selector.
The crystal does the selecting. Much simpler, and it turned out to be right.
And this simple idea led to, one of the most famous equations in physics, Bragg's law. Lambda udax 2b n var theta. Maybe unpack that for us.
Sure. It's beautifully elegant. The lambda is just an integer, like 1, 2, 3. Lambda is the wavelength of the X-rays you're using.
Okay.
Lambda is the crucial bit that's the distance between those atomic planes in the crystal.
The spacing.
The spacing. And var theta, that's the angle, the glancing angle, at which you shoot the X-rays onto the crystal face to get a strong reflection.
So it connects the wavelength, the crystal structure, and the angle you measure.
It ties them all together. If you measure the angle var theta where you get a bright spot, and you know the wavelength lambda rack, you can calculate the spacing inside the crystal.
And Bragg's father, W.H. Bragg, he built a device to actually measure this.
He did. The X-ray spectrometer. It was a clever setup using an ionization chamber, basically an early electronic detector, to measure how strong the reflected X-ray beam was at different angles.
Yeah.
Very precise for the time.
And they used this to figure out the structures of simple things first, like salt.
Exactly. Sodium chloride, potassium chloride, common salt, and its relatives. And that's where things got really interesting, chemically speaking.
Ah, okay. So analyzing salt revealed something unexpected.
Totally unexpected based on the chemistry textbooks of the day. They expected to find, discrete NaCl molecules packed together.
Right, like little pairs of sodium and chlorine atoms.
But the structure showed something different. The sodium and chlorine atoms were arranged alternately. Each sodium surrounded equally by several chlorines, and each chlorine by several sodiums. There were no distinct molecules.
So what did that imply?
It implied the atoms weren't neutral atoms bonded in pairs, but were actually ions positively charged sodium and negatively charged chlorine held together in a continuous lattice by electrical attraction. It fundamentally changed how people thought about ionic solids.
Wow. So mapping salt changed chemistry, but the tool itself, the spectrometer, was also pushing physics forward.
Oh, absolutely. Because by measuring the reflections carefully, they could also work backward. If they knew the crystal spacing dollars, they could use Bragg's law to precisely measure the wavelengths lambda of the X-rays themselves.
And they found that elements emit specific X-ray wavelengths.
Yes, the characteristic X-ray lines, people call them, the K radiations and L radiations. Each element had its own signature fingerprint of X-ray wavelengths when you bombarded it.
And measuring these frequencies this led somewhere even bigger.
It led straight to quantum mechanics, astonishingly. They took the frequencies they measured for these characteristic X-rays
Okay.
and combined them with results from other experiments, like Whittington's work, which measured the minimum energy you needed from, say, an electron beam to make an element emit those specific X-rays.
So input energy versus output X-ray frequency.
Exactly. And Bragg's father put them together and showed that the energy needed to excite the X-ray, E, was directly proportional to the frequency of the X-ray emitted, the constant of proportionality. Planck's constant, E equals nu.
The quantum law, applied to X-rays for the first time, experimentally proven.
The first solid proof for X-rays. It was a massive confirmation of quantum ideas. Energy in, quantum of light out, perfectly balanced.
And this ability to measure characteristic X-rays precisely, this then fueled other discoveries.
Hugely. It was a direct enabler for Henry Moseley's famous work. He used these characteristic X-ray frequencies to order the elements in the periodic table correctly, based on their atomic number, not just their weight. It sorted out all the kinks.
So this technique just kept opening doors. Bragg said it decreased the limit of scrutiny 10,000 times compared to a microscope.
Something like that, yeah.
Yeah.
It let scientists, as he put it, look into the interior of the molecule and the atom. A whole new scale of vision.
Which brings us sort of full circle. If X-rays diffract because they interact with the electrons in the atoms, then the next step, which Bragg himself pointed towards even back then, is using the same technique to map out not just where the atoms are, but how the electrons are distributed around them.
That's exactly where the field went, and where much of it still is. Once you know the basic atomic positions, the fine details of the diffraction pattern tell you about the electron density, how the electron clouds are shaped, how they change when atoms bond.
So they built the lens to see the atomic arrangement.
And now that lens is used to test and refine our quantum mechanical understanding of the electrons themselves. What does that electron distribution actually look like? That's the ongoing investigation.